At this point in your organic chemistry career, you probably feel pretty familiar with ethers. After all, we've used them a number of times in the lab as solvents or in various extractions. We've also, of course, seen them used in a variety of different reactions, generally as solvents in reactions when we don't want to use a protic solvent such as water or an alcohol. But what do ethers actually do? What do they actually look like? And why are they so useful as solvents? These are questions that we can answer when we take a closer look at the structure and the reactivity of our ether molecules. Now, first off, we need to define what an ether is. So an ether is a functional group that has an oxygen atom that's bonded between two different carbon chains. So we could have two identical carbon chains, such as diethyl ether, shown here, or of course we could have two different carbon chains. So we could have a single carbon chain and then a three carbon chain on the other side. Our example up here in the middle is a symmetrical ether, because of course we have identical symmetrical carbon chains on either side, and our ether over here would be unsymmetrical. Okay, now let's look at naming for our ethers. So our ethers can actually use a substitutive or a functional based naming system. And I'm going to go over both for you. For our substitutive naming, what we're going to do is we're going to find our longest carbon chain, excluding For our substitutive naming, what we're going to do is we're going to find the longest carbon chain on our ether overall. So if we look at our ether here, we have two carbons or two carbons. So our longest possible chain is a two carbon chain. So if we grab that two carbon chain, that would give us the name ethane. Right? So we're going to use ethane as our base parent name. We're going to name it as if it's an alkane. And then we're going to be naming the rest of this as a branch, a substituent, coming off of that ethane parent chain. So in this case, our branch has two carbons, but it also has our oxygen. So we take that oxygen, and we're going to call it a oxy group. And we have our two carbons. Two, of course, gives us our eth prefix. And this is going to be an ethoxy substituent. So this would be our ethoxy ethane with that two carbon ether substituent coming off of our ethane parent chain. So the general rule for the substitute naming system is that we are naming them as alkoxy alkanes. Right? We use the same naming system for our regular alkane parent chain, and then we're just adding on that ether group as an alkoxy branch coming off of our alkane. We could also use numbers here to indicate what carbon that's coming off of. So for example, if we had, say, a 4-carbon system with a oxygen bonded here with two more carbons coming off of that. So now this would be a 1, 2, 3, 4. So that would be a butane. And of course, our branch is at the second position. This is again a ethoxy branch. So this would be 2-ethoxy butane. As you can see, we can easily name both symmetrical and unsymmetrical ethers with this naming system. So we have our ethoxy ethane, or over here, our original unsymmetrical ether here. We have our propane as our longest parent chain. Our oxygen and our carbon are coming off that as a branch. And so this would be methoxy propane. For both my ethoxy ethane and my methoxy propane, notice I'm not including numbers because, of course, we'd always start counting from that first carbon that has my ether substituent on it. So these would both be 1-methoxy and 1 ethoxy for both of these two ethers here. The second possibility for naming our ethers is using a functional group-based naming system. So here we're going to explicitly state the name of our functional group in our overall name. So we're going to actually include the word ether at the end of our name to indicate that, yes, we have an ether in this particular molecule. And then to indicate what carbon groups are bonded to that ether functional group, we're going to name it as alkene branches coming off of our ether. So it's going to be an alkyl ether. So naming each of our alkene branches and then indicating at the end that it is an ether with these alkene branches coming off of this. So now we can go back to our same ether molecules that we showed before and take our slightly different approach here for our naming. So here we have two carbon branches coming off of our oxygen in our symmetrical ether here. So this is a diethyl ether. Again, of course, that's the name that I originally gave you earlier. That's the common name that we tend to use for this ether. Although, again, that 1-ethoxyethane is also appropriate as well. If I go over here to my 1-methoxypropane, according to my substitutive rules, so again, I split off each of these branches. We have methyl, we have propyl, and so this becomes a methyl propyl ether. So that naming system is relatively simple, just based off of what my carbon groups look like on either side of that ether. Now, our functional naming system gets a little bit more complicated for more complicated ethers, such as the 2-ethoxybutane that I show here. So now, again, we're going to be naming each of these as alkyl branches coming off of our ether. And so what that means is that my numbering, of course, is always going to start from my branching point. So I have my 1, 2 carbons here for my easy ethyl branch. But then down here, this is a branch that has a branch coming off of it. This would be my first carbon off of the branching point, second and third. And so this would be counted as a new methyl branch coming off of my propyl branch. So this branch would be a 1-methyl-propyl as my alkyl branch. And my full name then would be ethyl 1-methyl-propyl ether. So again, each of my 3 ethers here have 2 possible names, one based on my substitutive naming system and one based on my functional naming system. One of the things that you might notice here is that in general for smaller ethers, it's easier to use the functional naming system. For more complicated ethers, it can be easier to use my substitute naming system. Right? 2-ethoxybutane is a lot easier to work with than ethyl 1-methyl-propyl ether, whereas diethyl ether is simpler than saying 1-ethoxyethane. So both are equally accurate and both can be used. It's just a matter of your preference and also based on how complicated that ether is. Now, before we move on from our naming here, I do want to mention that our ethers, similar to our alcohols, also have a sulfur form of the same functional group. So we can have a sulfur bonded between 2 carbons. Again, of course, those can be varying carbon chains, just as for our ethers. And we call these sulfides. For our IUPAC functional and substitutive nomenclature, our sulfides are just called alkyl thioalkanes. So that would be for naming them as a substituent. So this would be an ethylthioethane. Or, of course, for the functional name, we again just use our alkyl, as with our ethers, but then end with the name of the functional group. So this would be an alkyl-alkyl sulfide. We won't go into any depth on our sulfides overall, but just as with our thiols versus our alcohols, they share a lot of similarities to our ethers. They're just going to be slightly different due to that larger size and slightly lower electronegativity of our sulfur. Next, let's take a look at the properties of our ethers. So our ether, of course, contains our electronegative oxygen. So that oxygen is going to be pulling electron density towards itself, as always. That creates the partial negative and partial positive charges. However, what we don't have here with our ether is we don't have any hydrogens connected to that oxygen. So we have no hydrogen bond donors here within our ether. And without any hydrogen bond donors, our ether then can't hydrogen bond with itself. So we have no hydrogen bonding then between our ether molecules, which then means that we're going to have relatively low boiling points and melting points. So we don't see our typical high boiling points and melting points that we see with alcohols with our ethers. Actually, our ethers tend to have fairly close melting points and boiling points to similarly sized alkanes. So they're very, very low boiling point molecules. And of course, we see that in lab, right? Every time we pull out the ether, I always warn you about how volatile it is. And of course, volatility is based on how easily it evaporates, or how easily we're able to pull apart these ether molecules and break those intermolecular interactions between my ether molecules, right? So without the hydrogen bonding, I've got some dipole-dipole interactions, and of course, my standard van der Waals interactions. But overall, it's relatively weakly held together. So all of our ether compounds tend to be quite volatile and can be easily evaporated or boiled with heat. Now, while our ethers are aprotic and don't contain any hydrogen bond donors, we do still have our hydrogen bond acceptor in the form of our oxygen here at the center of our ether molecule. So of course, since we have a hydrogen bond acceptor, that means that we can form hydrogen bonds with other molecules that are hydrogen bond donors. So that includes things like water, right? So water, of course, is one of our greatest hydrogen bonding solvents. We have our oxygen, our two hydrogens that act as two hydrogen bond donors, while our oxygen itself can act as two hydrogen bond acceptors. The water loves to make hydrogen bonds with other water molecules or with other molecules that we're trying to dissolve in water. So since our ether can accept hydrogen bonds, it's actually relatively water soluble. So we have decent water solubility, even though we don't have any hydrogen bond donors. So our ethers actually tend to be fairly soluble in nonpolar solvents, right? Because without that protic hydrogen bonded onto our oxygen, we're not as polar as something like water or an alcohol. But we're also still fairly soluble in water as well because of that hydrogen bond acceptor. So ethers really do mix well with a lot of different compounds, which again is another reason why we often see ethers used as solvents in the organic chemistry laboratory. Right? They dissolve nonpolar things really well, but they aren't terrible at dissolving polar things also. Now the last key property of our ether is of course based on this partial negative charge. So partial negative charge, that of course indicates that we are somewhat nucleophilic, or that we are a weak Lewis base. A Lewis base, of course, is something that is willing to donate a lone pair of electrons. This nucleophilicity or basicity of our ethers is very useful in these compounds we call crown ethers. So these crown ethers are compounds with multiple ether functional groups that are linked together in this cyclic system. So here we have a crown ether with 4 different ethers. You can also have much larger crown ethers where you link even more ethers together in these larger cyclic systems. Now each of these ethers, of course, again will have partial negative charges, and they're willing to share these excess electrons with other atoms nearby. In particular, we can use things like metal atoms. So if I take a metal, and I'm just going to designate this as M for a metal ion, and of course our metals tend to be positively charged, and they like to make those coordinate bonds where they share electrons with nearby electronegative atoms. So we can use our excess electron density of our lone pairs here, of our ethers, and we can form coordinate bonds and help to bond the metal in the center of this crown ether structure. Now as we change the size of this crown ether, we can actually change then what metals we can accommodate at the center of this ether, right? A smaller metal will fit in a small crown ether, such as this one, whereas if we add in more ether units, we can then fit larger metal ions in there, depending on how many of our ether units we have linked together. So this allows us to then bond specifically to certain metal ions and hold them inside of our crown ether. Now you might wonder, how is this useful to us, right? Who cares if we can bond that metal here in the middle of our ether? Well, one of the big things that this does for us is it allows our crown ether to act as what's called an ionophore. So an ionophore is a molecule that's capable of carrying a metal ion across a cell membrane and thereby transporting that metal ion throughout a biological system. So normally our cell membrane acts as a wall or a barrier because it's nonpolar. So any kind of charged or polar substances can't easily pass through that nonpolar membrane, and so they're essentially excluded from coming inside the cell. With our crown ether, so our ether itself is relatively nonpolar, but it's using the Lewis basicity of our oxygens to bond and hold that polar metal ion in the middle of our crown ether. So it's basically hidden inside of our crown ether. Our crown ether, since it's more nonpolar, is able to pass through that barrier of our cell membrane, since it's nonpolar and it can mix with that nonpolar cell membrane. And so we can then easily transport our ions into or out of the cell. So we can use this in experimental applications if we want to transport specific ions into cells that we're testing, but it can also be used in therapeutic roles as well, where we can use it to transport ions into a cell or outside a cell in order to carry out some particular effect on that cell. So ionophores are a very useful application of that basicity of our ethers, as well as, of course, the overall solubility of our ethers, in the sense that they're able to really dissolve and move around in a lot of different solvents. Now that we know a bit about the properties of our ethers, we can take a closer look at the reactivity of our ethers. Now, one of the things that makes ethers useful as solvents is that they actually tend to be relatively unreactive. So compared to our alcohols, right, we no longer have the oxygen-hydrogen bond, which is highly polarized and helps make our oxygen more nucleophilic. We also have this additional carbon bond that kind of adds some more crowding there as well and makes it a little bit harder for our ether to react. So generally they're relatively unreactive. However, they do have a few different reactions that we'll see. One of the reactions that's very common for ethers is actually our combustion reaction. So they're highly flammable. Again, of course, I mentioned before how they are similar to alkanes in terms of their boiling points and melting points, while they're also similar to alkanes in that they do tend to combust. Right? So again, when we bring out ethers in lab, I mention how volatile they are, but I also generally mention how flammable they are as well. Right? So you do have to be a bit careful when you're working with ether-based solvents. You don't want to be exposing them to heat unless you know that they're not going to be catching on fire very easily there. while our ethers are relatively unreactive, we are going to take a look at a couple different reactions that we see with ethers. So the first is going to be a condensation of alcohols in order to form ethers. So this reaction will start, of course, with our alcohol. So here I'm going to use ethanol, and we're going to react it in the presence of acid with excess of our alcohol. So this is actually going to be a standard substitution reaction with two alcohols. So we're going to take our alcohol and react it with our acid. So of course, as usual, acids can protonate alcohols in order to make alkyloxonium ions. So we have our good water leaving group here. And now, of course, at this point, we can bring in, we're going to bring in a second unit of our alcohol to act as the nucleophile, right? As soon as we create that good leaving group, then we're ready to react with the nucleophile. So we can attack on here and break off our good leaving group. That leads to our protonated ether, which can then be deprotonated to form our ether product. And of course, as we're bringing in our water to deprotonate it, that is going to be regenerating our acid. So again, our acid just acts as a catalyst here, and we generate our ether as our final product. So this is, of course, just a SN2 reaction between two alcohols. There's nothing really new about this mechanism. We're just applying it to make our ether here, as opposed to usually where we see this reaction between alcohols and alkyl halides. Here it's going from an alcohol to an ether. Now I will say that this reaction is really only suited for making symmetrical ethers, right? If you try to make an unsymmetrical ether here, so then you'd have to add two different alcohols together, right? So we might add propanol and ethanol. But the problem here is that you're never going to have just one molecule of propanol reacting with one molecule of ethanol. So you're going to have a bunch of molecules of propanol and a bunch of molecules of ethanol, and at that point you could then have the propanol reacting with itself, so you'd end up with some of your propyl-propyl ether produced, you'd end up with some of your ethyl-ethyl ether, and you'd also end up with some propyl-ethyl ether. So you'd end up with a mix of products instead of your desired propyl-ethyl ether product, or ethyl-propyl ether rather, to put those in alphabetical order. So you really only want to do this with just one alcohol present, adding that acid and creating a symmetrical ether. Otherwise, you just get a messy mix of products, and it's going to be hard to actually purify your desired product from this mixture of very similar looking ethers. The other thing that's important to note about this condensation reaction is that it's not likely to work for a secondary alcohol or a tertiary alcohol, such as the secondary alcohol reaction that I show here. Right? So you might expect that if we use the secondary alcohol, you could have the reaction mechanism just like I showed before to produce our isopropyl ether, our diisopropyl ether. But the problem here is that at this step here, we're also going to have a competing reaction of an E1 elimination. Right? So this could break off and form our carbocation, and at that point then we can use our water that we produced from our leaving group there to deprotonate and form an alkene product. So generally we don't tend to use this sort of condensation approach with secondary and tertiary alcohols because there we get a lot of competition from our elimination reaction. So it's really best used with just primary alcohols and then producing, of course, only those symmetrical ethers. Now this sort of substitution reaction of our ether can also go in the opposite direction. So once we form our ether, we can actually break it apart using an acid cleavage reaction. So if we take our ether and we're going to react it with a hydrogen halide, I'll use HBr in this case, although of course it could be other hydrogen halides depending on what alkyl halide products we want to form. So again, this is going to follow our typical substitution mechanism. So first we have to protonate our oxygen as always, and then that's going to create a good leaving group. We're going to create an alcohol leaving group instead of a water-based leaving group. So we have now our leaving group in the center of our molecule. We also have our bromide, which acts as a good nucleophile. Right, so now we can take our nucleophile and attack while we break off that leaving group, and we're then able to create an alcohol along with an alkyl halide. Now, depending on how much of our hydrogen bromide we add, we can also react further with our alcohol. So we can take that alcohol, react it with a second unit of our hydrogen bromide. Again, we just protonate that alcohol, produce our alkyloxonium with our good water-based leaving group now in this case. And we can use our good bromide nucleophile to attack in a substitution reaction as we break off that leaving group. And this would end up producing a second unit of our alkyl halide product, as well as, of course, our water leaving group here. So again, this is something that we'll generally want to do with a symmetrical ether, because otherwise we get two different alkyl halide products that might be difficult to separate. But it's going to allow us to break apart that ether, form alkyl halides, and then of course we have access to all of our usual alkyl halide reactions. So as we see here, our ethers aren't super reactive, right? They don't have a ton of different reactions that we do with them. We can convert them to other functional groups if needed, and then we can use the reactivity of those functional groups. But generally, the main role of our ethers is just as great solvents, right? They tend to be one of the most common solvents that we use, other than, of course, water or even things like acetone. So that tends to be the main role of ethers rather than their reactivity, and that lack of reactivity actually becomes a benefit for our ethers, again, because we can use them as solvents without generally worrying a whole lot about the ether itself interfering with our reaction.